right, here we go. Lesson 9.4 notes. Welcome. Advanced algebra notes on graphing sine and cosine functions. So this is going to be a part 1 video. Obviously, you could tell that by the title by looking at it, but we'll get through the first part here of what do these parent functions look like of a sine and a cosine function. We'll do a little bit as far as transformation go. We'll take care of the stretch and shrink part in this video in part 1, and then in the second video we'll do the translate and reflect the graph. So let's jump in, let's get it going, let's lay some groundwork here. So we've got our parent function y equals the sine of x, same input output. What are we inputting? Angle measures, really in radians is pretty much exclusively what we're going to work with, our angle measures, but we could take the sine of any angle, and then the output is the actual sine of that angle. So for our graphing purposes, we're going to work with, we can look at them here. these angles, for the most part, when we make our parent function here in a second, and these should look familiar. Like we've seen these before. These are kind of our big ticket angles, what we call the quadrantal angles. So we're going to make an old school kind of XY table. X is my, if we want to kind of define what the heck is X, remember we just said it a second ago, but X is theta in radians. So we're basically going to input angle measures, and we're going to take the sine of them. And the kind of the cool part, or at least the connected part to what we've done before, we're not just hammering these numbers into our calculator and converting from radians, degrees, all that stuff. We've seen these quadrantal angles, and hopefully we remember that when we're on our unit circle, I've got these, sorry, I was trying to get them all on there without screwing them up. We've got these are our angles, right? So I mean, as far as, well, I'm not going to put all that, it's just going to get too cluttered, but we should remember that, hey, here's our 0 radians, and by the time we work all the way around, 2 pi radians. So between this figure and the connection, and knowing that when we're on the unit circle, the y coordinate is equal to the sine of an angle, we can fill this entire table in, all 9 points here, just with this information. Okay, so I'm going to kind of start in the middle, and then maybe we'll work the positive angles, then we'll go back to starting in the middle and work the negative angles. Okay, so 0 radians, where am I? I'm right here. What's the sine? What is the y coordinate of this location? 0. So the 0 radians, the sine is 0. We move up. We're basically moving, remember, in quadrantal, we're moving in increments of 90 degrees. So my next stop along the way, my next big quadrantal angle is right here. So 90 degrees, or pi over 2. What's my sine? It's the y coordinate, 1. Okay, and we kind of just move our way along the, whoops, I didn't mean to do that, the unit circle here. My next stop would be right here. And then the sine is the y coordinate. We're back around to 0. I keep traveling along. I'm down here at 270, or 3 pi over 2 radians. My sine is -1. And then I'm right back where I started. This spot, 360 degrees, or 2 pi radians. And my sine, my y coordinate, is 0. So you can kind of see, like, that's not terrible as far as where are these coming from. Like, hey, we did that in previous lesson. Going the other way, right? So these equate to 0 degrees, 90 degrees, 180, 270, 360. Well, we could start at 0 and just move the other direction, and we get those same numbers, except they're negative angle measures. So if I start here, 0 radians, 0 is my sine. I back up 90 degrees, negative pi over 2, my sine. My y coordinate is -1. We keep traveling another 90. Oh, my new y coordinate is 0 at negative pi. I go a -3 pi over 2. My sine is 1. And I get back around where I started, -360, or -2 pi. A y coordinate of 0. So that's kind of how we built the table, or not kind of, that's how we built this table of 1s and 0s. Those are our major angles. So to actually graph it, so hopefully we made this table in our notes, we're going to actually make the graph right here. We're going to plot, let's see here. I'm going to try to see if I can do this. with keeping it still readable, and where I line up my y-axis, like still our normal old x and our y-axis, okay? But I'm trying to, actually I'm going to extend this just a little bit, and hopefully we can still all see it, that my x-axis here, and I'm going to try to align my graph with my table. I'm putting tick marks at all these major angles. Okay, so what I mean by that is like this would represent pi over 2. This tick mark here represents pi. This tick mark represents 3 pi over 2. So they're equally spaced. Each degree, each tick mark represents moving 90 degrees or pi over 2 radians on our unit circle. And really, I only need, I guess you could argue, 3 different outputs on the y-axis. Obviously, we know an output of 0 right here, but an output of 1, we're just going to somewhat arbitrarily, 1 is my output, my max output, and then as long as I kind of move about that same distance down here, -1. Why is that it? Why is that all we need? Because we don't get any bigger than 1. The big 1 is the biggest output we ever get, and -1 is the smallest output we ever get. So all the numbers, our entire graph is going to fall within this region. Okay, so the last part is now putting these points on the graph. Let's do the positives again. So 0, so see if you can follow me here. 0, we'll use a different color though. 0 radians is 0 sine, right? Remember y, what we can say this here is that's our sine of theta, and x is theta in radians. Whoops, that's supposed to be a little theta. Okay, we can put a 0 here too if we want. My next angle measure was pi over 2. So at pi over 2, where were we? At pi over 2, we were all capped out up here at 1. Actually, you know what? I'm going to go through and just label my axes, or my x-axis. I guess my y-axis is already labeled. Just to kind of, I mentioned it, but I didn't actually put them on the graph. So all I've done was just transferred all these angle measures down to my graph. All right, now let's do it. Let's use a different color though. Let's plot them. 0 radians, 0 sine. Pi over 2 radians, 1 sine. Pi radians, 0. 3 pi over 2, we're down at -1. And then at 2 pi, we're back around to 0. Okay, we go the other way. I'm at negative, whoops, didn't mean to do that. Negative pi over 2, we're down at -1. At negative pi, we're back up to 0. At -3 pi over 2, we're all the way up at 1. And then at -2 pi, we're back down to 0. So you get these random like dots. And what ends up happening here is I'm going to connect it with a nice smooth, no sharp lines, no points, no jagged edges. Just a nice smooth curve, kind of flowing through all these points. I am going to put arrows on the ends just to make sure we know, or let my readers know, which are you, that we're choosing to stop right here, right? Like this graph doesn't just stop right here. This graph would continue to, extend forever to the right, to the left. We just chose to stop after 1 revolution positive and then 1 revolution negative, but we could continue to make more and more and more and more and more and more revolutions, and it would extend this graph. So there's what our parent sine graph looks like. A little bit of vocab going on here. I think we can just add it. We did it in class. We just added it right to our graph. We don't need all this, but the big thing that I would say we should add would be to what's known as the period. Okay, and the period is essentially how the distance, not time, but the distance that it takes for the graph to repeat. So if I look here, I started at 0. I'm kind of counting from here. I go up, 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 max out, back down, 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 down. I'm still not repeating yet. These points have never come up on the graph. All these negative signs, and then finally I get back to right here is where I'd be like it's my equivalent starting spot to right here. Okay, so that's what's called a period. How long is our period? Our period is 2 pi radians. That's how long it takes for this graph to completely repeat itself. Same thing, this distance from right here to right here before the graph starts repeating again would be 2 pi radians. And then the other one I think we need to add here is what's called the amplitude. We'll work with these a lot in the second part of the lesson. But the amplitude essentially is the absolute value, or amplitude, and our amplitude is 1. So amplitude is kind of what would be like considered like the midline of the graph, up 1 unit this way, 1 unit down that way, or in the negative direction. But we would just say it has an amplitude of 1. Our amplitude should always be positive. Okay. There's a few things that I mentioned here. The range, domain, well, range at least, and we'll talk about domain here in a second. But maximum, minimum values 1 and -1. So there's our sine parent function. Just kind of put a pin in it for right now. Like that's what we need to know. That's what this graph looks like. Yeah, for now until we start translating and reflecting. All our sine graphs are really going to be just versions of this, either just stretched out vertically or shrunk or stretched horizontally. But they're going to have these same basic features, okay? Let's go through that same process here with cosine. Hopefully we can go a little bit quicker because it's very, very similar as far as how we're making the graph. We're still going to use those same big quadrantal angles. Okay, so I think we can get our table filled in maybe a little bit quicker here. I'm going to go back to that same, I can't see it, so I need to see this picture here, right? Our unit circle with all these major intersections here, 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 and here. So I've got 1, 0, 0, 1, -1, 0, and then 0, -1. Except now, instead of looking at the y coordinate, hopefully everybody remembers that we need to be looking at the x coordinate because that's what goes with the cosine of an angle. That's the only difference as far as process and how we're going to be doing this. So let's start in the middle again. 0, here's 0 radians. My x coordinate's 1 there. I jump up here. My next landmark, my x coordinate's 0. I jump over here. My x coordinate's -1. I jump around to 3 pi over 2 and back down to 0. And we always finish where we start. We started at 1. We finish with 1. While we're here, we might as well just kind of reset and say, all right, I'm at 0 radians. Let's back up negative pi over 2. Let's back up another pi over 2. Back up another pi over 2. And back around to where we started, negative pi over 2 going this way at 1. Okay. All right. Making the actual graph, ton of similarity. I'm going to do that same thing. We'll go quicker here. In that, I still think it's, at least for now, whoops, I'm going to kind of change color here. We got y, which remember now is our cosine of theta. Whoops, cosine of theta. And if I extend this as much as I can, x, we're calling, well, I'll write it over on the side because we're a little bit further. X-axis is theta in radians. Okay, I need tick marks, even as best I can. I'm just kind of freehanding it, evenly spaced. Might as well just label everything right away. Pi over 2, pi, 3 pi over 2, and 2 pi. Going the other way, we end up with, let's get the tick marks first. 4 evenly spaced, negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. All right, we need, just like before, our largest output value is 1. Our lowest, let's see, same distance-ish. Our lowest output value is -1. We've got our 0, I guess we could stick here on our x-axis. And it's a matter of now plotting these points. And you can see that, I mean, we're going to take on, after we plot them here, that we're going to end up with very, very, very similar shape. Let's see. 0 radians, output is 1. Pi over 2 radians, output is 0. Pi radians, output is -1. 3 pi over 2 radians, output is 0. And 2 pi radians, cosine is 1. So we're kind of, just like we said, back where we started. I follow the same pattern here. Negative pi over 2, we're down to 0. Negative pi radians, my cosine is -1. Back to negative 3 pi over 2, my cosine is 0. And we finish where we started at negative 2 pi, back up at 1. So when I graph it, I have that same smooth curve. All right. And that's what our cosine graph looks like. Totally similar. And if you're just kind of glancing one or the other, it's hard because I got to scroll here. You're like, what the heck's the difference? These are the same exact graphs, except one's just kind of slid over. And yeah, they look the same. They're just it's one's kind of slid a little bit. So there we go. Same basics. I don't know if we have to relabel our period. Well, let's just take a look. Our period is still the same. That same 2 pi. So for how long does it take this graph to repeat? That's that distance, right? If I kind of cut it off here and here, we're going to see it's kind of weird because you get like a half of an upper little section, then we get a full lower section, then another half. That's that other half of the upper section, but that's still a full period. So our period is still 2 pi. That's worth putting, I guess. And then our amplitude is still hasn't changed. It's still 1. Just abbreviate here. All right, awesome. So I think we've talked about all these characteristics here. So I don't know if there's anything else we need to add to our notes. Domain, I'm not going to ask you a ton right now about domain and range, but domain would be all real numbers, meaning that there's not a single angle measure that we couldn't plug in there, that I couldn't find. You couldn't give me an angle measure and say, oh, that's too big. I don't know what the sine of that is. Or sorry, that's too small. I can't find the sine or the cosine of that. Like, you're going to be able to find the cosine of any angle that you could think of. Super big, super small. Range on these parent functions we just saw is never changing. It's always the lowest it ever gets is -1, and the largest it ever gets is 1. So our range is from -1 to 1. Amplitude we talked about. There's this kind of a fancy way to say it: 1/2 of the difference of the maximum and minimum values. We should just kind of count from the midline up or down, doesn't necessarily matter. And this is essentially, again, kind of a little bit more formal way of talking about what we call the period. But knowing that each period or each graph has a period of 2 pi is, I think, kind of good enough for us right now. Okay. X-intercepts are repeating, but there's a lot of them, and we won't get into that notation. So yeah, I think we're okay there. Nothing really need to add for our notes on that section, I don't think. All right. So, obviously the parent functions are one thing, but we're going to do stuff to them. You can see what's coming here. We've got stretches and shrinks. So like I said, day 1 notes that we're watching right now, that's all we're doing: stretch and shrinking, no translations or reflections. So the 2 things we're looking out for that's going to cause a stretch or a shrink, it's the same kind of letters we've seen in the past. Any number being multiplied, kind of what we look at is in front of the sine or the cosine function, is going to basically take our output, whatever the sine cosine is, and multiply it by a number. That's the number that's going to stretch us or shrink us. How do we know if it's a stretch? If the number a is bigger than 1, that's going to stretch us. It's going to shrink us if that number is between 0 and 1. Same rules as we had going back to chapter 1. Horizontal stretch. The reason I have this one set up down here, it's kind of foreshadowing a little bit. We're going to see, here's the translation stuff, the H and the K, which I know we've seen before. But really what we're looking out for is the B. It's the number, if we want to think about it really informally, the number in front of the X, like we'd see here and here. But we could potentially see it, we will see it eventually, like this. And you might think, well, couldn't you just distribute the B and then you'd have the B right in front of the X? And that's absolutely correct. So however I see it, if there's a number outside, like a group of parentheses like this, that's the same B, it's the same number, it's going to do the same horizontal stretch or shrink. And you kind of covered up everything that I wanted to talk about there. But that's the one that's the reciprocal, the 1 over B. So if I see something like this, y equals 3 times the cosine of 2x, that's going to be a vertical stretch by a factor 3, right? What I see is what I get. But then this is the one that it was actually a horizontal shrink because the B must have been 1/2, and then I flipped it over, right? This is how you flip something over. I use the reciprocal of it to get this 2 right here. Okay, so we'll practice that here a little bit. The last skill I'd say we need, we're going to cover right here in this notes, and then it's a matter of, all right, how do we apply it? How do we use it? Okay, so that's a little bit of just kind of what we're looking for. We're looking for numbers in front of the cosines or sines, and then numbers in front of the x's. All right. All right, here we go. New heading, identifying a function's period and amplitude. So these are the two things that we need that I'm going to ask you to do when it comes to graphing is tell me what the amplitude is, tell me what the period is. So you can see the two functions. They're written the same way we just saw them. The number in front is going to tell me the amplitude. Okay, so we'll do them one at a time. Here's how you find the amplitude. It's the absolute value of that number. So we'll see here if it's a negative number, like here, it's really just the positive version of this. So but that one's for most people are really easy to recognize. It's the number in quote unquote in front of the function. So when I look, let's see here, let's just go through each one and identify the amplitude. So definitely set up, pause it, set up your example, see if you can do it before I do it. Amplitude. These are just kind of mini examples. We'll get to example one here in a second, but hopefully this is not blowing anybody's mind. Amplitude 3. Okay, 3, sweet, awesome. Amplitude 2, the number before the sine of the cosine. This one, the lower left here, C, we say with -5, I just said it a second ago, my amplitude, we would still say is 5. And then here, right, it's like a little 1. If I don't see a number, the amplitude would still be, it's still there, it's 1. We just don't see it. What are these negatives going to do? That's going to cause our reflection over the x-axis, which, again, we won't see till the next lesson. Okay. Last thing before we move beyond amplitude, this is going to, for us, for right now, it's going to how we're going to, let's just say this, use to, what do I want to say? Use to label y-axis, just for now. Again, kind of just putting a pin in that, and we'll come back to that here in a second. We're going to use that. I'll show you how to use it here in a second to label the y-axis. For period, there's actually a little bit of a calculation. Like we're going to do a division. So it's always, we're going to take the normal period of the parent function, 2 pi, we wrote it twice not too long ago, and divide it by the absolute value of b, okay, whatever that number is in front of the x. And that's my horizontal. The reason we're dividing is to kind of undo that, what we just saw a second ago, that shrink or stretch factor that was 1 over b. So that's kind of the idea behind it there. So, but it's actually a process of 2 pi divided by whatever that number is. So let's switch colors here and do period. So for each one of these, I need to go 2 pi divided by, in this case, 1/2. That can be clunky. That's the same thing as multiplying by the reciprocal. So it's really 2 pi times 2 over 1. So if you're kind of, I'll write this first one out. This could be thought of as, if I want to do this without a calculator, remember division is the same thing as multiplying by the reciprocal. So for me, it's easier to do that without a calculator. I can do 2 pi times 2 essentially, which is 4 pi. So our period for this for part A here would be 4 pi. For the second one, it always kind of starts the same way. Take the original 2 pi, divide it by this b. That one's just a matter of reducing it, so we can write this one, I think. The period is 2 pi over 4, which once I reduce it is just pi over 2. Okay. Jumping down here, we're going to use 2 pi. If we can, I'm going to just kind of write over the top, because to be honest with you, this right here for right now doesn't matter. This right here doesn't matter. That's going to be our translation, left and right, but coming up in future lessons. So for right now, I just need to, for period identification, I need to take 2 pi and divide it by 2/3, which is the same thing as 2 pi times 3 over 2, which is 6 pi over 2, which is 3 pi. Okay, I know I'm going quick on there. I'm trusting that you guys can handle crunching that, either whether it's calculator or like we're showing here. And then for the last one, it's 2 pi divided by 2, right? That's my number right there. I didn't mean to cross it off. 2 pi divided by 2. So we end up with a period of just of pi. Okay. So again, that's more skill-based. What are we going to use that for? Why don't we do that? Make the exact same note right here. We're going to use that right here to use to label x-axis. once we know the period. Okay, so once I know this period, I'll show you how to use that to label the x-axis. Okay. All right. Well, we're about ready here to do it. So these are kind of the big ticket questions for the day one assignment, day one concepts. I did put together a little just kind of informal. How do you graph a sine cosine function without a shift? So definitely pause, add to your notes if we're going to talk through these. I don't know if I'm going to come back and directly follow this, because it's not necessarily a like you got to do this first, you got to do this second, you got to do this third, but we can come back and maybe like after we do one, I'll just talk through it, and then maybe we can come back and see, oh yeah, let's do this, let's do that. So yeah, let's take a look. Let's jump into one here. All right, because all it's asking me to do is I need to, it should say graph one period of this right here. So I'm not asking you to make a bunch of them, but one period of this. So where do we start? What's the first thing we should do? The first thing I see is why don't we just identify? I'm asking you for two things. Tell me the amplitude and the period. So those same two skills that we just were working on. Why don't we just get those done? So I look at this and I see, hey, that's got an amplitude of 2. That's my amplitude. For my period, we say, hey, take 2 pi, divide it by this number that's in front of the x, and say, all right, 2 pi divided by 4. Let's reduce that. It's one that we just saw, right? Pi over 2. Okay, great. So far, so good. So I guess that does align with the first thing I said to do. I'm not saying you have to do that first, but identify the amplitude and the period. Got it. I'm going to do actually the y-axis next, just because it goes with the amplitude. So this amplitude is telling us now, instead of going up, on a parent function, we kind of go up. The max of output is 1 and -1. Well, now my max outputs are really 2 and -2. So whatever this number is, that's going to take those max outputs and multiply it by the amplitude. So if I lost you there, really what I need to do is just break my y-axis up into increments that's going to get us here to the amplitude. Okay, so you can see my amplitude was 2. Instead of going up to 1 like the parent function, I'm going to go up to 2, and then I'm going to go down to -2 when it comes time to make the graph. Here's kind of the cool part about this, at least until we start translating, that I'm going to break my x-axis up into 4 equally spaced tick marks. So again, I'm kind of going back and forth here, but divide the period into fourths, label the x-axis. That's kind of what we're doing right now. All right. So the only difference between this and the parent function, instead of this being 2 pi, my period now has been basically cut down significantly. Instead of a full 2 pi, we're getting this whole graph made in pi over 2. But for our sake, we're just essentially going to zoom in. So I don't want to lose you here. I want to take the new period, what we figured out to be, and that's what I'm labeling this last tick mark with. Okay, and I've got my same freebie, the 0 here. Okay, so it's very similar to our, if I can scroll back, let's find our sine one. And just focus on kind of the first quadrant. Whoops, didn't mean to lose everything there. Or the positive angle measures, right? We had 0, we had 2 pi, and then we had 1, 2, 3, 4 evenly spaced tick marks. So a ton of carryover here, right? Like where it's, all right, my amplitude, fine, we're going to 2 and -2. Instead of going 0 to 2 pi, we're going to go 0 to pi over 2. Okay, and because everything's equally spaced, I basically just need to divide this pi over 2 into fourths, and that's kind of where this 4 is factoring in here. Cut it up 4 ways. So let's do it. So here's how I do it. It's up to you. There's different ways you could get this. If the stronger we are with fractions, the easier this will be to follow. But basically, I'm going to jump to this middle increment here and say, well, I want what a number that's halfway between 0 and pi over 2. So what you can do is just take the full period, right? The full period is pi over 2, and literally cut it in half. How do you cut something in half mathematically? You multiply by 1/2. You could say divide by 2, but then that's going to get Maybe not so nice on the simplify. So what's pi over 2 times 1/2? Straight across the top, straight across the bottom. Great. Halfway between 0 and pi over 2 is pi over 4. Okay, sweet. Now I want halfway between 0 and pi over 4, right? Because we're equally spaced, so I just need to be right in between here. So I'm going to do the same thing. I'm going to say, let's take this pi over 4 and now cut that in half. So straight across the top, straight across the bottom, pi over 8. The third one's always kind of the toughest one, and it depends. I mean, maybe my definition of tough is different than yours, but what's halfway between pi over 4 and pi over 2? I can't just it's not as easy as just cutting something in half again. So there's different ways to get there. I'll tell you what I do. I'll show you two different ways. I usually just count, now that I know each increment is pi over 8. So it's like this is pi over 8. This is another pi over 8. This is another pi over 8. This is another pi over 8. I can just count by this first increment. So 1 pi over 8, 2 pi over 8, 3 pi over 8. And then if I follow my same logic, this should be 4 pi over 8, which 4 pi over 8 reduces to. So that's one way to do it, is just count by whatever the increments are. Some people, they lose. I lose them on that one. So I would say maybe this is 3/4 of the way here. So you could go back to, all right, I want 3/4 of, remember math, in math, of means multiply. I want 3/4 of the full period, which that's the full period. So I multiply straight across one more time, 3 pi over 8, and we get to the same spot. So it's up to you how you're going to come up with that, but we got to be decent. This is kind of where all the point value lies as far as the type of problem on a quiz or a test, is being able to label your x and your y axis accurately, identify your period amplitude, which you have to do to label this accurately. And then the last part, so now let's go back and kind of look here. So I think we've labeled that y-axis, divide the period into fourths, label the x-axis, amplitude, period. I say use the unit circle to decide where to start. And I'll show you what I mean by that. So it's basically, I'm going to clear this. Hopefully we've got that all in our notes. If not, go back, rewind it a little bit and re-add them. So when I say use that unit circle, it's that same picture we just looked at. Where does sine start? Like when I go to make a graph, this is the point 1, 0. Does sine, remember sine is the y coordinate. Where does sine start? Sine starts at 0. The y coordinate starts at 0 and then goes up to the maximum. Okay, start at 0, go up to the maximum, right? Because this point would be 0, 1, and 1 on a parent function is the maximum. So if I start at 0 and go up to the maximum, that's for me, and hopefully for you too, that means start at 0 on my graph. I'm talking up and down now. The output, start at 0 output, but then by the time you get to this first landmark, we need to be up at the maximum. So my new maximum now is 2. And if we kind of have an idea of how this works, each landmark, you got each horizontal, I say landmark, each horizontal landmark, each big angle, we need to hit the equivalent vertical landmark. So 0 maximum, 0 minimum, 0, if I could keep going, maximum, 0 minimum, 0 maximum, 0 minimum. And there is my period. Okay. And like I said, if you were to flip back and look at that parent function, I still got it. It's identical. It starts at 0, goes up. If you ignore all this stuff here, take this out of it, take all these numbers out of it, these angle measures out of it, it's the exact same graph, right? All we really did for ours, so we're kind of cheating the system a little bit, I think, where we're kind of hacking and just saying, let's just zoom in a little further and keep the exact same graph, but just kind of change our scale to fit our graph. That's exactly what we're doing. All right, let's at least do a cosine for sure. I'll do a cosine, an example B, and then I'll do just a kind of a different look for checkpoint 1 here. So, but we can go quicker. It's the same process for sine, cosine. So when I look at this, let's do the amplitude right away. It's 3 pi over 2. I'm going to label everything right away. Why not? So I see this. One thing I'd ask you to do is try to stretch your graph out vertically and horizontally as much as you can. I don't like the graphs that are like that. Say, hey, look at that graph. Even though it might be accurate, it gets hard to kind of read all that stuff. So stretch your graph out. I'm going to go by like halves basically, because if this is if my absolute top here is 3 over 2, this can be 1 over 2 and then 2 over 2. So I'm going by halves basically. 1 half, 1, 3 halves, 2 if I were to keep going. And then same thing going the other way. -1 half, -1, and then -3 pi over 2. So hopefully you follow me on that one. I'm going to even before I find the period, I could go through and divvy this up equally into fourths. All right, we've got our 0 here. I can label that one. That one's not changing because we're not translating. And all right, what's the next number I need is what's my period? How long does it take for this cosine graph, which actually is going to start up here, to finish? Okay, well, I got to do it. I got to go 2 pi divided by the number that's in front of x. Okay, pi. So pi over pi cancels. This one's kind of unique in that my period is 2 radians, not 2 pi. That's the first time I think we've ever seen a radian measure that doesn't have a pi attached or associated with it. So, okay, fine. 0 to 2 is my is our period. So from here, it's basically, all right, I kind of like that because I don't have to worry about pi. What's halfway between 0 and 2? 1. What's halfway between 0 and 1? 1 half. Just use fractions. We're already using so much with fractions where you wouldn't really see decimal increments. And same thing, you could still count at 1 over 2, 2 over 2, 3 over 2. Or you could go, I want 3/4 of the full period and get 6 over 4, which reduces to 3 over 2. So it still applies. I was just showing you that same technique of using the 3/4 we can use right here as well. So, all right, everything's labeled. I like it. The last part is use our, where does this graph start? And this one's not necessarily tricky, but it starts. So now we got to think x-axis wise, because cosine, when we're on the unit circle, is associated with the x-coordinate. So the x-coordinate, this cosine graph starts totally maxed out on the parent function at 1. That's 1 is the max output. So for us, for our graph, any cosine graph we're making, we want to start at the max possible output, which for us would be right up here. Okay, we follow that logic there? Because the very first, and you can go back and look. Oh, is he going to go back and look again? Holy cow, Mr. Kroll. Where does my cosine? Let's use the nice, well, ours is pretty good. Where does a cosine graph start? It starts maxed out here right up at the top. Kind of drops in, hits our increments. Max out, 0. Minimum, 0. Max out, 0. Right? So I kind of like that, saying it to myself. I get to see what's going on. So max out, 0. Bottom out, 0. Max out, 0 if I were to keep going. But I'm only asking for 1 period, so it's a matter of now getting our graph made. And I think we've covered everything. Once you get the hang of it, they actually go kind of quick. I know we kind of flew through that one a little faster, but we've laid the groundwork, I think, that I don't know if we necessarily have to, what am I asking you to fill in? Amplitude and period. Well, amplitude's almost a gimme. We use that to label here. Period, a tiny calculation here. And then it's all kind of just boils down to labeling. I think, to be completely honest, I think the spot where people struggle the most is knowing, do I start low and go high, or do I start high and go low? and it's just going to take some practice. For now, cosine always does this. Sine always starts here and goes up. So that'll all change as soon as we learn some more stuff. Let's do the last one. I promise you. Last example for the notes here. Same deal, same everything. Amplitude is 1/4. Let's do that same process. So one of the things that for a lot of the different chapters and everything, graphs, is I always try to make them the same. So I always am going to start with my amplitude just because I think that one's kind of easy to do. This one, depending on, I mean, let's see, how do we want to label this? What's a good way we could split this up? Because it's almost arbitrary, but let's see, if I called I need like a little bit more room if I were going to call each one of these tick marks a fourth. Yeah, well, sorry. You know what? Let's just do this. Let's call this one right here can be a fourth. This can be -1/4. And like I said, it's almost arbitrary. That means we're basically going by eighths. And I don't want to lose everybody there. All right, but it's like 1/8, 2/8, 3/8, and it's going to fill me up a little bit more versus just calling this first tick mark 1/4, then half, then 3/4, then 1. That means my graph's only going to do kind of a tiny little thing here. So don't get crazy hung up on that. We just need to know, like, hey, that's my ceiling, 1/4 amplitude. All right, I'm going to pre-lay out my 1, 2, 3, 4 equally spaced tick marks on the x-axis. We know that this is 0. I just need to calculate what is 2 pi divided by, 2/3. But even this one, I still think we did earlier when we were practicing all this stuff. This is the same thing as 2 pi times 3/2. So multiplying fractions straight across, 6 pi over 2, which is 3 pi. I'll just jump down here and drop it in. So there's my 3 pi. Great, awesome, I love it. Cut that in half. How do you cut 3 in half? You divide by 2, and we could just leave it exactly like that. So half of 3 pi is 3 pi over 2. This might be one. I don't know. If I need to, I don't think that one just screams like, oh, I can cut that in half. What's half of 3 pi over 2? I want half of 3 pi over 2. So 3 pi over 4. That's a little different. And even this one now, you say, well, Mr. Kroll, you said you just count. I got to count by 3 pi's over 4. So counting by 3 is almost in my numerator. 3 pi over 4, 6 pi over 4, 9 pi over 4, which is what this is going to be. Otherwise, go back to and just do, hey, you know what? Mr. Kroll said I could also go take the full period, and I want 3/4. Whoops, 3/4 of it. I don't mean that to be in there. So what's 3 pi times 3? 9 pi. 1 times 4 is 4. Hey, look at that. 9 pi over 4. So the hardest part about this one, I would guess, is probably coming up with those numbers, keeping the pi's in there, keeping the fractions in them. We don't want 0.75. We don't want 1.5 for these numbers, okay? So get used to using the fractions with the pi in it. Last part is just deciding, okay, sine. Maybe at this point, you're already like, well, I made the parent graph. It started at 0, 0. We did the first graph with sine. It started at 0. And you can bet that if I were to look here, this sine graph is going to start at 0. Let's see. Go up to our maximum, 0, minimum, 0. So 0 max, 0 min, 0. And there we have it. So we'll definitely break there. That covers that's quite a bit. I mean, it's a longer lesson. We broke in class at that point. There's a day 1 assignment that goes with just that, with just really making kind of these quote unquote simpler graphs where it's just stretching, just shrinking. Although we're kind of taking that out of it, right? We're kind of taking it. They never look stretched or shrunk, but that's because we're modifying the scale around them to make them to make our kind of our normal graph fit on the scale. So that's what's going on there. So definitely we've taken care of the characteristics part of it, some of the basics, the parents and stuff like that, and we've looked at the stretch and shrink. So stay tuned for part 2 that has the translate and reflect components to it. So that's all I got for you here. We'll call 9.4 good, and I'll see you in future lessons.